Hi students, and welcome to this lecture which is dedicated to the study of logarithms. Log tables have been used for making some of the very complex calculations since the ancient times. So in this lecture we are going to study what are logarithms, what are some of the very important properties of logarithms, and through some of the solved examples we are going to understand how to apply these properties in solving problems. Also we are going to study about what is characteristic and mantissa. So without wasting a moment, let's try to understand what do we mean by logarithms. Suppose we have an equation a to the power of x is equal to m. Here a is known as the base and x is the exponent. What is m? M is the value of this expression, which is a to the power of x. Now as we are studying about logarithms, let's try to see how we can write this exponential equation into a logarithmic form. So in the logarithmic form, this could be written as log m to the base a is equal to x. So in the logarithmic form, this exponential equation becomes log m to the base a. A is known as the base, which is equal to x. Remember that this very x is actually the exponent of a. So in the logarithmic form, the log of m to the base a would be equal to x, and x is the exponent of the base in the exponential form. This could well be written as this way. If we have this logarithmic equation, we can reduce it to this form. So this equation literally means that a to the power of x is equal to m. X is the exponent of the base a. So x is equal to the logarithm of m to the base a. So in the exponential form, this equation is a to the power of x is equal to m. And in the logarithmic form, this equation could be written as log of m to the base a equal to x. We always calculate the log of any number m to the base a. Base has got a lot of significance. So in general we can say that logarithm of a number to a given base is the power or exponent to which the base must be raised in order to produce that number. So what is logarithm of a number? We always define logarithm of a number to any particular base, and it is actually the power or the exponent to which the base must be raised in order to produce that number. This number of whose logarithm we are trying to find. Now let's take an example to understand this. We have an equation 1000 equal to 10 cube. We always know that 10 cube is equal to 1000. Now this is an exponential equation. If we want to convert it into a logarithmic equation, this would be log of 1000 to the base 10 is equal to 3. So you clearly see that it is actually the logarithm of 1000 to the base 10 is the exponent to which this base must be raised in order to get this number 1000. So 10 should be raised to the exponent 3 so that we get 1000. So in general we can say that if x is equal to a to the power of y, then y would be equal to log of x to the base a. So this is how we convert an exponential equation to a logarithmic one. If x is equal to a to the power of y, then y would be equal to log of x to the base a. Now there's something very important to note. If we have log of m to the base a equal to x, then for log to be defined, a should be greater than 0 and a should not be equal to 1. So for log to be defined, the base should always be positive. It should always be greater than 0 and its value should never be equal to 1. This is very important. Log is never defined for negative numbers and the value of base should never be equal to 1. Also, logarithm of a negative is not defined, so m should be greater than 0. So logarithm of a negative number is never defined and thus we get m greater than 0. So for log to be defined, the base must be positive number, that is it should be greater than 0 and it should not be equal to 1. Also the logarithm of a negative number is not defined, so for log to be defined we take the values of m to be greater than 0. Now we usually use a base of e, which is a natural constant. So in many of the cases you would find that the base is taken to be e, and this e is known as the natural constant. The number e is approximately equal to 2.718281828459 and so on. So it is an irrational number which is non-terminating and non-recurring. So E is approximately equal to 2.7182 and so on, and this is a natural constant. In general, we use the base as equal to E. And also you should know that in cases where the base is taken to be E, it is denoted by ln x and not log x. The logarithm we usually use is log base E. So we take the base to be equal to E, and it is written as this way, log x to the base E, or often we use ln x, and this is called as the natural logarithm of x. So whenever you find the word natural logarithm, quickly you should know that base is taken as E. Also, at times the base is not given, it is simply written as log x. Then in such cases you got to take the base as equal to 10, and that is known as the common logarithm. So natural logarithm has the base equal to E, and the common logarithm has the base equal to 10. Now we shall see some of the very important properties of logarithms. Now these are some of the very fundamental properties, and I want you to learn them by heart. The first is, if c is equal to log a to the base b, then this would mean that a is equal to b to the power of c. Now this is a logarithmic expression which has been converted into the exponential expression. So if c is equal to log a to the base b, then a is equal to b to the power of c. The second is, ln of x to the power of y is equal to y times ln x. Here ln x means that the base is equal to e and y is the exponent of x. So ln of x to the power of y would be equal to y times ln x. So it is simply the exponent of x multiplied by ln x. So in general, if we have log of x to the power of y when the base is equal to a, then that would be equal to y times log of x to the base a. The third property is, log of r into s base a is equal to log of r base a plus log of s base a. So if we have to find out the logarithm of product of two numbers, then that would be equal to the logarithm of the first number plus the logarithm of the second number, and the base is the same, a. So the log of rs to the base a would be equal to log of r base a plus log of s to the base a. The fourth is, log of r by s to the base a is equal to log of r base a minus log of s base a. So now if we have the number as division of two numbers, then this could be written as log of r minus log of s. That is the subtraction of log of two numbers. So log of r by s to the base a is equal to log of r base a minus log of s base a. The next property is, log of p to the base a is equal to log of p to the base x divided by log of a to the base x for any x, and this property is known as change of base. So simply what we see here is that we have changed the base and we have written this expression as a division of these two terms. The first term is log of p to the base x and the denominator is log of a to the base x. So simply we have changed the base from a to x. The next property is, log of p to the base a is equal to 1 by log of a to the base b, and this property is known as the reciprocal property. So here the bases have been reversed. Here on the LHS the base is a and on the RHS the base is b. So if we want to convert log of b to the base a in terms of base b, then that would be equal to 1 by log of a to the base b, and this property is known as the reciprocal property. The next property is, a to the power of log of x to the base a is equal to x. Here log x to the base a is the exponent of a. Note that this number and the base both have to be same, and this would be equal to x. Similarly, log of base is a to the power of x and the number is b to the power of y, then this is equal to y by x into log of b to the base a. So in the LHS, x is the exponent of the base and y is the exponent of the number b, and in the RHS this would be equal to y by x into log of b to the base a. Now you should remember that log of 1 to the base a is equal to 0 for all a greater than 0 and a not equal to 1. So for all the values of a such that they are greater than 0 and none of them is equal to 1, then log of 1 to the base a would always be equal to 0. And this is very important. Always remember that log of 1 to any base a is always equal to 0. The condition is a should be always greater than 0 and should not be equal to 1. Let's look at the proof of this. Let us say that log of 1 to the base a is equal to x. Let us say that this is equal to x. Now in the exponential form this would be equal to a to the power of x equal to 1. So we have a to the power of x equal to 1. Now 1 could be written as a to the power of 0. We know that a to the power of 0 is always equal to 1. And so we get a to the power of x equal to 0. Now when we compare both the sides, what do we get? We get the value of x equal to 0. So what do we get? We get the RHS as equal to 0, and so the LHS would also be equal to 0. Thus we get log of 1 to the base a is always equal to 0. The condition is a should always be greater than 0 and a should not be equal to 1 for log to be defined. The next important property is log of a to the base a is always equal to 1. So when the base and the number both are the same, then log of such a number to the same base would always be equal to 1. Again, the condition is for log to be defined, a should be greater than 0 and a should not be equal to 1. So again, let's look at the proof of this. Let us say that log of a to the base a is equal to x. Now in the exponential form, this would be a to the power of x equal to a. Now the RHS could be written as a to the power of x equal to a to the power of 1. And when we compare the LHS and the RHS, what do we get? We get x as equal to 1. And so this would be equal to 1, and thus log of a to the base a is equal to 1. So always the log of any number to the same base is equal to 1. So these were some of the very important properties of logarithms. You got to remember them, and through examples we are going to understand these properties more clearly, how these properties are used in solving many of the problems based on logarithms. But before that, let's try to understand the graph of ln x. So this represents the graph of ln x. Ln x means that the base is equal to e. And this is the natural logarithm. And this is the graph of e to the power of x. It is in the exponential form. So this represents the graph of e to the power of x, and this represents the graph of ln x. Remember that both of them are inverse of each other, and so both these graphs are symmetrical about the line y equal to x. Now we are going to focus only on the graph of ln x. Now there are some of the very important points that we got to note in this very graph. So the important facts are ln x is always defined for x greater than 0. We have seen that log is always defined when the number is greater than 0. So for negative numbers, logarithm is not defined. And this is clearly visible from the graph of ln x. We see that when x is less than 0, this graph is not defined. So this graph entirely lies on the right hand side of 0. It is also not defined at x equal to 0. So for values of x which are greater than 0, ln x is always defined, and for values less than equal to 0, ln x is not defined. So from the graph you can clearly see that ln x is always defined for x greater than 0. The second important point is ln x is equal to 0 at x equal to 1. So at x equal to 1, value of ln x is equal to 0. And ln x is an increasing function. Now what is an increasing function? Increasing function means that the value of the function increases as the value of x is increased. So here the value of x is increasing, and you can clearly see that the value of ln x is also increasing. So for an increment in the value of x, see that there's an increment in the value of ln x. So ln x is always defined for x greater than 0. Ln x is equal to 0 at x equal to 1, and ln x is an increasing function. So when x increases, the value of ln x also increases.